what is an elimination matrix? So now we have to talk about types of matrices. Let's first talk about the identity matrix. Then let me show you how to get to a lower triangle matrix, and then you will understand what we mean by elimination matrices. Let's say we have this square matrix. We want to factorize this matrix. We want to extract from this matrix the L matrix and the U matrix. To get to the U matrix, we must first do the L matrix. To get to the L matrix, we need a sequence of elimination matrices. Here's the idea. In the previous example where we use Gaussian elimination, yes, we did those row operations, but we did not keep track of which numbers we used or what order we used. Well, I guess you could say we kept track because here I have replaced R2, but that's not what I mean. When I say keeping track of the operations, I mean having a matrix or a collection of matrices that says you did this to row 1, and then you did this to row 2, and then you did this to row 3. And these are written in matrices. Now, what do I actually mean? Let me show you. So I'm going to keep this here, and I'm going to open LU decomposition.ipynb. Okay. Once again, I will import numpy as np. And then I'm going to recreate this matrix. The first thing we are going to do is, what we want to do is, again, we want to get to upper triangular form, right? So we want this to be 0, and then these two to be 0. Okay, this to be 0, this to be 0, this to be 0. And everything across the diagonal should be a non-zero value. How would we get rid of -3? That's the first thing we need to make 0. Well, let's see. One way to get rid of 3 is to first multiply this row by 3. So this would become 3. This would become 6. That would become -9. But we don't care about these two. What's important to us is that if we multiply this row by 3, then we could add these two together. 3 plus -3 would cancel out row 2. And as far as we're concerned, that's considered elimination. Now, I can use the same code I did in the other file, S0 plus S2, but that's Gaussian elimination. We don't want to do Gaussian elimination. Okay, let me show you what I mean. Now, this I will denote as A. And then I'm going to create a matrix called np.array. This is going to be the identity matrix that I've been talking about. What's in the identity matrix? You have a square matrix that is the same size as the matrix to which you want to multiply this identity matrix. And we have these values. Basically, an identity matrix is a matrix with zeros everywhere except across the diagonal, the main diagonal. Why is it called identity matrix? Let me show you. I will show you the result of this evaluation, and then I'll show you a picture. I'm going to go np.matmul. This is short for matrix multiplication. So I'm going to apply the identity matrix to the original matrix. When I multiply this, you can see we get the same matrix again. I mean, it's the same thing. How is this possible? So I'm going to pull up a picture of matrix multiplication. This is a good example. The way you would multiply two matrices is you would multiply, well, the first number in the first row times the first number in the first column of the second row. If you look at the picture, you should get the idea. And then the sum of these two products, so 2 times 3, 0 times 4, that would become the first value in the resulting matrix. By arranging the numbers in identity matrix, like what we just saw, we will get back the same resulting matrix. You can take a second or two to look at this. So 1 times A, and then 0 times C, and then 0 times E. Well, you see these zeros, right? These zeros are going to cancel out the other terms, and all you left is 1 times A. And 1 times A is just A. Look at this so that you're convinced that the identity matrix will give you the original matrix.